This is part 3 of the lectures covering vectors. We now take a look at two-dimensional vector addition. Okay, let's immediately begin by copying down the next problem from the handout or the document called Lecture Examples. Go ahead and take a moment to copy that problem down into your notes. I'm going to go ahead and read it here. Okay, a student walks 3 meters to the east and then 4 meters to the north. How far from the origin is the student's final position and in what direction? So far, the only means that we have available to us of adding the vectors together is graphically by using the tail-to-tip method of vector addition. When I did this in the previous lecture for the one-dimensional case, because it was a one-dimensional case, it really wasn't necessary for me to use a ruler to measure out all the distances. Here, however, in this two-dimensional case, I do have to do so. In order to define the two-dimensional coordinate system, however, we have to reference, first of all, exactly what directions are north, south, east, west. We typically represent those directions in the following way. So west is to the left, east is to the right, north is upwards on this simple diagram, and south is downwards. Okay, now I'm going to go ahead and draw, using a ruler here, my two-dimensional coordinate system for this problem. Like so. Okay, and then we have our first vector, which is 3 meters to the east. I'm going to think of this as the vector A. Now, using my ruler, obviously I can't draw a vector here that is 3 meters long because I don't have enough board space. So instead what I'm going to do is I'm going to say that 10 centimeters on my ruler here corresponds to 1 meter in the problem. Therefore, for the vector A, 3 meters to the east, I have to draw a vector here with a length of 30 centimeters. And let me go ahead and use a different color in order to do so. All right, so 30 centimeters long. That'll be from 10 to 40 here on my ruler. Like so. And there's the vector A. Okay, and now I'm going to add to that a second vector. We'll call it B. This is going to be 4 meters to the north. So then therefore, I have to point my ruler like so along the positive y-axis, and then I have to draw it 40 centimeters in length. So in my case, I have to draw that from 40 to 80. That looks like this. So right here is the vector B. Okay, and then the resultant goes from the origin to where I ended up. We're going to call this third vector here the vector C. A plus B. Let me also take a moment here to write down the magnitudes of the first two vectors. A is 3 meters and B is 4 meters. Okay, and now the vector C is drawn from the origin to where I ended up. Once again, we're using a tail-to-tip method of vector addition here to add these two vectors together. So that's going to be drawn like so. So from the origin to this point, right here, like so, there's my resultant. That's the vector C. Now, in order to find its magnitude, what I have to do simply is I need to measure its length here by using my ruler. So right here on the diagram, like so, is the length of this vector, the vector C, and its length is about 5 meters. Like so. But then I also have to determine its direction. In order to determine its direction, I'm going to go ahead and measure an angle associated with the vector C. I'm going to do so by using this protractor. So I'm going to line up my protractor like so on my coordinate axis, such that this is parallel to the x-axis, and this right here is pointing at 90 degrees. This is with respect to the y-axis. And then I just simply measure over this angle here on the diagram, and in doing so, it's maybe about 54 degrees or so. Like so. Now, I was pretty careful to add these two vectors together to get the resultant by using my ruler, for example, to measure distances, using this protractor to determine this angle, but of course what you just saw me do is prone to measuring error. So how do I get around this problem? How do I add the vectors here in 2 dimensions instead analytically? Well, in order to get around the problem of measuring error, we add the vectors together here analytically by taking advantage of a little bit of right triangle trigonometry. Notice that there is a right angle here on this diagram, even though I didn't indicate it as such. Because we have the size of this side of the triangle, keep in mind that this was 3 meters, and the size of this side of the triangle, this was 4 meters. Notice that the resultant, the vector c, is nothing more than the hypotenuse of this right triangle, so then therefore we can use a little bit of Pythagorean theorem. So here's how the Pythagorean theorem would be written for this example. We have here 3 squared plus then 4 squared is equal then to the hypotenuse squared c squared, like so. Think of the hypotenuse here as having a length c. So then therefore, if I punch this out on my calculator, I can then go ahead and find the magnitude of c. So I take 3 squared, which is 9, plus 4 squared, which is 16, add those together to get 25, and then I have to take the square root. When I take the square root, we always use the positive answer. And the reason for that is because we're finding the magnitude of c, which is only a size. It's only a positive number for that reason. So the square root of 25 is just simply 5. So c is equal to 5 meters. So my measurement here, of course, was pretty good, but it is prone to measuring error. This answer here, however, is exact because we're using an analytical method to solve for it by using some right triangle trigonometry. We could also find the angle here on the diagram as well. Let me now go ahead and call this angle theta. So recall the basics of SOHCAHTOA. Okay, specifically when finding the angle here, we're going to use the tangent. The reason for that is because the tangent of the angle theta is equal to the opposite side of the triangle, 4 meters, divided by the adjacent side of the triangle, 3 meters. We're using this portion here of SOHCAHTOA. So tangent of theta is equal to the opposite side 4 divided by the adjacent side 3. Now this is the ratio itself. In order to go from the ratio to the angle on your calculator, we have to use a specific button on the calculator in order to do so. Okay, now I have a Texas Instrument calculator, and then on the calculator is a button for tangent of course, but then written above it is the symbol tan with a -1. This quantity here above is referred to as the inverse tangent. The inverse tangent right here is what I need to go from the ratio 4/3 to the angle. On my Texas Instruments calculator, here's what I then type in. I hit the second key, which allows me to get to this point here, and then I hit the tan button. And then I type in the ratio of 4 divided by 3. Doing this in degree mode on my calculator, when I hit then enter, this then gives me the following. It's about 53.1 degrees. I'll go ahead and round it off to 53 degrees as the answer. Like so. So my measurement of 54 degrees up on the top board was pretty accurate, but it isn't exactly precise. Whereas this answer here is much more precise because we're finding the answer analytically. Okay, let me go ahead and erase this example. While I'm doing that, let's then go ahead and take a look at the second problem. I need to call it up here on my screen. Okay, now because with this second problem, I'm going to solve this problem analytically, I'm not going to be as careful as I was in the previous example to write out everything with a ruler and a protractor and so on. Sketching this by hand is going to be good enough because all I'm going to do is solve the problem analytically. So in this case, the student walks 5 meters to the west and then 12 meters to the south. Okay, so that roughly then looks something like this. So here's north, south, east, west, and we begin by first of all walking 5 meters to the west. So we'll say that roughly looks something like this. We'll call this the vector A. So A equals 5 meters. Okay, and then we'll add to that B, which is 12 meters to the south. That roughly looks, say, something like this. So here's B. B is 12 meters to the south. And then therefore the resultant, the vector C, that then looks like this on the diagram. So the vector C is equal to A plus B. There's two things we need to find about the vector C. First of all is its magnitude. In order to find its magnitude, we once again just use a little bit of Pythagorean theorem. So in this case, we're going to have 5 squared plus then 12 squared is equal to C squared. And then once again, we just solve for C, the positive value, here on my calculator. So I have 5 squared plus then 12 squared. Take the square root of all of that. And the answer then ends up being a magnitude of 13 meters. By the way, those of you that are already familiar with a little bit of basic trigonometry from your mathematics classes may recognize that in these two examples we have the following simple right triangles. In the first example, it was nothing more than a 3, 4, 5 right triangle. In this example here, it is what is referred to as a 5, 12, 13 right triangle. But in addition to finding the magnitude, we also have to find the direction. I'm going to find the direction by defining this angle here on my diagram. Let's call this angle theta. Once again, I'll use a little bit of tangent in order to find the angle theta. The tangent of theta is equal to, first of all, the opposite side of the triangle, 12, divided by the adjacent side of the triangle, 5. Once again, I have to go from the ratio to the angle, so I have to use the inverse tangent button on my calculator in order to do so. So then therefore I have the inverse tangent of opposite over adjacent, 12 divided by 5, and that ends up being about 67.4 degrees. Like so, as the answer. When you do a problem such as this, however, you always want to make sure that you draw a diagram as I've been doing here, and then exactly indicate on the diagram what the angle is that we're trying to find. In this case, this angle right here is 67.4 degrees. When it comes to two-dimensional cases involving motion in this class, we will only look at situations involving right triangles. So because of that, we need to use Pythagorean theorem to find magnitudes of vectors, and we also need to use a little bit of right triangle trigonometry to find an angle, such as we did in these two problems. Okay, that concludes this lecture on two-dimensional vector addition.